Artificial intelligence is rapidly reshaping how societies function, driving innovation, efficiency, and economic growth across industries. Yet this same technology raises serious ethical and socioeconomic concerns. Issues such as bias, privacy, accountability, job displacement, and inequality remind us that AI is not neutral. This module introduces AI as a double edged sword, a powerful tool with the capacity to both benefit and harm society. Our focus is on understanding these trade offs and why ethical thinking must accompany technical advancement. We would like to thank you for your interest in the NSFK grant Expanding Use Inspired AI Research and Instruction Across Campus. And here is the copyright notice. We explain here why ethical and socioeconomic awareness in AI is essential. When AI systems rely on biased, incomplete, or unverified data, the consequences affect real people, shaping access to healthcare, education, financial opportunities, public safety, and trust in organizations. Understanding these risks early is key to building and evaluating AI systems that are fair, transparent, reliable, and accountable. This slide highlights an ethical dilemma in the healthcare case. A risk scoring model allocated fewer resources to Black patients, even when their clinical needs were greater. This algorithm wasn't trained to measure illness, it was trained to predict future healthcare costs. But because Black patients often receive less care even when they're sicker, their costs in the data are lower. Figures 1 and 2 show that at the same risk score, Black patients actually have worse disease markers. Figure 3a shows the model predicts cost accurately. Figure 3b shows the real cost. Black patients generate less cost for the same illness level. So the algorithm learns a harmful pattern: lower spending, lower risk, when in reality, lower spending reflects reduced access, not better health. This slide highlights an ethical dilemma from the education case. Models penalize certain demographic groups not for weaker ideas, but for writing patterns shaped by their educational experiences. Table 4 reports QWK, which is just the overall accuracy score comparing each model to human graders. All three models look strong here. Table 5 introduces three fairness measures. OSA asks whether the model is equally accurate for each group. OSD checks whether the model scores some groups higher or lower than humans on average. CST goes a step further and asks whether those differences remain even when students have the same true writing ability. Using these measures, we see that some groups consistently get larger errors. Table 6 helps explain why. Features the models rely on, especially word count, vary across these groups for reasons tied to their educational experiences, not their ability. So the models end up penalizing certain writing styles simply because they are more common in particular groups, not because the ideas are weaker. That's the core ethical dilemma. This slide highlights an ethical dilemma in the finance case. Credit algorithms can reinforce racial inequalities by learning patterns from historically biased financial data. Table 1 shows that racial groups come into the credit system with different financial profiles. Black and Hispanic borrowers have lower average FICO scores, higher loan to value ratios, and higher default rates. These differences in the data are what the model learns from. Table I4 shows that these statistical models can predict race with surprisingly high accuracy using only financial variables like FICO, income, loan amount, and interest rate. Even though race is not included in the data, the model reconstructs it from correlated variables. This matters ethically because once a model can infer race, it can reproduce racial disparities even without explicit racial inputs. Table 7 show how these learned patterns translate into different predicted default probabilities and credit outcomes for each group. The model assigns higher risk to Black and Hispanic borrowers, even when they have similar financial characteristics to white borrowers. As a result, acceptance rates are lower and interest spreads, SATO, are higher for these groups. These unequal predictions become unequal real world credit decisions, reinforcing the same disparities that existed in the historical data. This slide highlights an ethical dilemma in the marketing case. Ad delivery algorithms can reinforce gender inequalities by allocating opportunities based on cost optimization learned from historically biased advertising markets. Table 2 shows men receive more ad impressions than women across all age groups, especially ages 18-44. Women have higher click through rates, meaning the gap is not due to lack of interest. So a gender neutral STEM ad ends up being shown much more to men. Table 3 shows using regressions with country fixed effects, the authors show that women are still significantly less likely to be reached by the ad. The largest deficit is for younger women. The imbalance cannot be explained by country size, population, or usage. So, Table 3 proves the gap is systematic, not a statistical accident. Even when you hold everything else constant, women still see fewer ads. Table 7 shows suggested bid prices, the cost to reach each demographic, are higher for women than for men, especially higher for women aged 25 to 44, meaning advertisers must pay more to show ads to women. So the algorithm shows more ads to men, unintentionally creating gender bias. This slide highlights an ethical dilemma in the public safety case. Facial analysis systems that misclassify darker skinned women at disproportionately high rates pose risks of misidentification, unfair targeting, and unequal treatment when used in policing, surveillance, or other public safety applications. Table 2 breaks down subjects by gender, FFM, skin type darker, lighter, and their intersection. Key points. The dataset includes 44, 6% women, and 55, 4% men. Skin tone distribution is 53, 6% lighter and 46, 4% darker. Importantly, 21. 3% are darker skinned females, a group almost missing in older benchmarks. Africa has very high representation of darker skinned individuals, while Europe is predominantly lighter. Table 3 compares the PPB dataset to IJBA and Allianz, showing that earlier benchmarks were overwhelmingly composed of lighter skinned individuals. 6% lighter, Allianz 86, 2% lighter, and severely underrepresented darker skinned groups, especially darker females. This matters because models trained or evaluated on skewed datasets will appear highly accurate simply because they are tested on the groups they see most often, masking large accuracy gaps for underrepresented populations. Figure 4 plots the confidence scores of IBM's classifier across four subgroups. Lighter male, confidence near 1. Lighter female, confidence near 1. Darker male, confidence high, but more variability. Darker female, confidence significantly lower, with many values dropping into the 0.75 range. Why this matters? Lower confidence aligns with the high error rates reported in the paper. The figure visually demonstrates that even when labels are correct, the system is least certain about darker skinned women. So commercial gender classifiers perform worst and with least confidence for darker skinned females, the very group most underrepresented in earlier datasets. In conclusion, AI affects people in every sector, from healthcare and education to finance, public safety, and business. When models learn from biased or incomplete data, the harm isn't always visible, but it can be significant and unfair. These dilemmas remind us that without careful design and oversight, AI can reinforce existing disparities. But they also show the potential for AI to improve equity, safety, and decision making when used responsibly. By understanding these risks now, you'll be better prepared to build and evaluate AI systems that are fair, transparent, and accountable.